Hello and welcome to lecture 11 for the course ECE 252B, Computer Arithmetic for Spring 2020. In this and the next three lectures, we will discuss the operation of division. So with this part, the main operations add, subtract, multiply, divide will be completed. And then later on, after we talk about floating point arithmetic, we'll also consider the operation of square rooting, which nowadays is considered to be a basic operation. So square rooting is really the last basic operation that we will discuss a bit later on. So in this part 4, dealing with division, the chapters have a similar structure to those in the multiplication part. So we'll have today in this lecture basic division schemes, chapter 13, then high radix dividers, chapter 14, lecture number 12. Lecture number 13 will be variations in dividers. And lecture number 14, dealing with chapter 16, will be division by convergence, which is a method quite different from all the other methods we discuss in the first three chapters. And in fact, it's one of the most commonly used fast division schemes in modern computers. So we'll see why. Okay, so let's get into basic division schemes, which are based on shift subtract, just as multiplication was based on shift add algorithms dealing with one bit of the multiplier at a time. Basic division schemes are based on shift subtract algorithms, generating one bit of the quotient per iteration. Okay, and just like we did in multiplication by constant, we will do the special case of division by constant, special algorithms for dividing by constants that are faster, more efficient than a full-blown division process. Okay, so this is our starting point for discussing division algorithms. So this is a division of an 8-bit binary number shown here. So that's called the dividend z, divided by the divisor d, producing the quotient q and a remainder s. I call the remainder s rather than the commonly used r because throughout this book and this course we use r to represent the radix, the number representation radix. So to avoid confusion, I'll call the remainder s. Okay, so the division equation is this. The remainder is z minus d times q. So given z and d, we perform the division but come up with q, so that d times q is approximately equal to z. Okay, when z is not divisible by d, then there will be a remainder s, which is a fairly small value. So d times q basically is almost equal to z. So when we divide z by d, if the division is exact, in fact, we get the quotient q, so that d times q is exactly equal to z. When the division is not exact, we are left with the remainder. So z is a 2k-bit number. D is a k-bit number. The quotient q is a k-bit number. And the remainder s is a k-bit number. So here we multiply a k-bit number by a k-bit number, we get a 2k-bit number. Z itself is a 2k-bit number. We do subtraction. And because these two are fairly close to each other, the result will be representable in k-bits. Each of these is 2 k-bits wide, but their difference is a k-bit number, which is the remainder. Now, to do the division, basically we subtract different amounts from the dividend, which is also the zeroth partial remainder. And each of these subtractions is done consistent with the choice of the quotient digit. So when we choose this quotient digit to be 0, then 0 will be subtracted. When we choose the quotient digit to be 1, then the divisor d. So this 4-bit number here is either 0 or it's the divisor d. And then when we choose the next quotient, so notice that this quotient digit is in the 8th position. It's worth 8 units. That's why this value has shifted to the left by 3 bits. The next quotient digit is in the 4 position. That's why this multiple of the divisor is shifted by 2 bits. This one is 2, worth 2, shift by 1 bit. And the last bit of the quotient is in the 1's position, so there's no shifting. So that's why these numbers are aligned as they are. So this will be subtracted from the 0th partial remainder, and at this point we get the first partial remainder after that subtraction. From that first partial remainder, we subtract this next number, we get the second partial remainder. Then the third partial remainder, and finally the fourth partial remainder, which is the final remainder. So these numbers that you see here are basically the product of the chosen digit. Let's say the first one is Q3 times D times 2 to the 3. 2 to the 3 is that 3-bit shift. And it's there because this bit, the weight of this bit is 2 to the 3. Then Q2 times D times 2 to the 2. Q2 times D times 2 to the 2. 2-bit shift, and so on. So these are the values that are subtracted. Okay, so basically if we knew all of these values, subtraction is essentially the same as addition of complements. So this would be very similar to multiplication, because instead of subtracting these one at a time, we could subtract all of them at once, do a multi-operand subtraction basically. However, these values will not become known to us until we have chosen the quotient digits. And that's one of the complications of division, why it is a harder operation than multiplication. So we first have to decide what this quotient digit is before we know what this number is. Then we have to decide what this quotient digit is, the next one, before we know this number. So ahead of time, we don't know these numbers. We have to generate them one at a time as we decide on the quotient digit values. And therefore, this is an inherently sequential process. We can't design the way we did for a tree multiplier, a 3 divider. Okay, so that will make the division also a slower process because we don't have very fast dividers as we had multipliers. Okay, so here is basically a catalog of the differences between division and multiplication. So we have an extra element here, which is quotient digit selection, that we did not have in multiplication. We need a process, an algorithm, for deciding what the next quotient digit should be. Also, whereas the product of two 4-bit numbers is always representable as an 8-bit number, going backwards, the division of an 8-bit number by a 4-bit number does not necessarily produce a 4-bit number. So we may have an overflow. Imagine that this 8-bit number is pretty large. Let's say 200. Okay, 8-bit numbers, unsigned numbers go up to 255. So let's say this number is pretty large, 200. And this number is 3. Okay, 0011. Then 200 divided by 3 is 66 and change. And 66 is not representable as a 4-bit number. Okay, in that case, we say that the division has generated overflow. So whereas we did not have any overflow in multiplication because the product of two k-bit numbers is always representable as a 2k-bit number, the ratio of a 2k-bit number by a k-bit number is not always representable as a k-bit number. So we need an overflow check. That overflow check is pretty simple. The high order k-bits of Z must be strictly less than D. So I only have to look at these 4 bits. The high order k-bits of Z must be strictly less than this. So if this were 3, as I said in the previous example, 0011, these 4 bits should be less than 0011. They can't even be equal to 0011. So they can be, for example, 0010. In that case, there's no overflow. Okay? And this also automatically detects divide by 0, because if this number is 0, then these 4 bits cannot be less than 0. At best they can be equal to 0. But equal to 0 is not sufficient for avoiding overflow. And less than 0 is impossible. Therefore, just checking that these k-bits, upper k-bits, represent a smaller number than this dividend, avoids overflow and avoids divide by 0, both of them. Okay, these are latencies from a fairly old processor, but not much has changed in terms of ratios of the times needed for these operations. So Pentium 3 had a 3-cycle load store instruction, a 4-cycle integer multiply, a 36-cycle integer divide. Notice that division is 9 times slower than multiplication. Okay, and similarly in floating point, multiply and add require a few cycles, divide requires many cycles. Furthermore, in that same machine, if you perform a multiply in 4 cycles, you can actually pipeline the multiply so that every cycle a new multiplication instruction can be issued. So if you have a lot of multiplications to perform, effectively you pay just 1 cycle per multiplication because they're pipelined in the hardware. Whereas no pipelining is possible the way the divide unit is designed. Doesn't matter whether you do 1 divide or many divides, each of them takes 36 cycles. Now there are 2 reasons for the divide being much slower here. One is, of course, the fact that division is inherently a more difficult operation. Okay? But the second one is also it's less frequently used. Therefore, we are not as motivated to speed up division as we are for multiplication. Multiplication is a very common operation in many applications, including in signal processing, whereas division is a rarer operation. It's not as frequently used. Therefore, investing a lot of hardware into making the divide faster may not make sense. It's not a good trade-off, okay? So 2 reasons. It's not as useful as frequently used as multiply. The second one, it's inherently more difficult to implement. Therefore, it turns out it tends to be slower. So just remember that add and multiplications in modern processors are roughly of the same order of complexity in terms of nowadays we can do add, multiply, whether it's floating point or fixed point in 1 cycle. Okay, so things have improved since Pentium 3. So add and multiply take 1 cycle in the fastest microprocessors. If you're talking about the lower speed microprocessors, maybe add takes 1 cycle and multiply takes 2 or 3 cycles. Okay, still, it's a fairly small number of cycles. Divide typically takes tens of cycles. Okay, so that's just round numbers to remember. 1 or a few cycles for add and multiply, tens of cycles for divide. Okay, just as we did for multiplication, instead of shifting these values by different amounts and then subtracting, we try to avoid that variable shift by doing the following. So we take the zeroth partial remainder, shift it to the left by 1 bit before subtracting this next value from it. So when we shift it to the left by 1 bit, that 1 bit goes past this boundary here. And then we subtract. Then the result of this subtraction is shifted to the left by 1 bit before we subtract the next one. So we avoid the variable shift. The shifting is always by 1 bit to the left because in each step, the previous value is shifted to the left by 1 bit before incorporating the next value. So this is represented in this recurrence. The jth partial remainder is the left shifted old partial remainder. So 2 times sj minus 1 means left shifted by 1 bit. Minus qk minus j, because the quotient digits are developed from this side, from the high end. Qk minus 1 is developed first, qk minus 2 next. So if this is S0, j is 0, then we compute S1 by subtracting qk minus 1, which is this digit, times 2 to the k times d. Okay, what is 2 to the k times d? 2 to the k times d is basically this value shifted to the left by k bits, so that it's aligned with the upper half of this number. Okay, so initializing the zeroth partial remainder to z, the dividend. After k iterations, we have obtained the k quotient digits, and we have obtained not the remainder, but to the k times remainder, because these left shifts, eventually there will be k of these left shifts. So the remainder, which would normally appear here, will appear here. But that's just a matter of basically interpreting it, even though it appears here, interpreting it as if it appears here. There's no corresponding right shift algorithm for division. So there's just one algorithm with left shifts, specified in this recurrence. The jth partial remainder is twice the j minus first partial remainder minus the next quotient digit times the left shifted d value, this one. I previously referred to this one as d. I made a mistake. D is here. Okay, so these are unsigned integers. So I was dealing with unsigned integer division. So right at the outset, we left shift z to get 2z. So one bit of z goes here, and a 0 is attached to its right hand. So this is now 2 times z. This is 2 to the k times d. It's aligned with the upper half of this 2k bit value. It's actually 2k plus 1 bit if you count this one as well. And then the subtraction occurs, a k-bit subtraction. And we repeat this process. Now we can also do fractional division by using pretty much the same recurrence. And the way to see this is that when you have z equals d times q plus s for integer division, if you multiply both sides by 2 to the minus 2k, so this is multiplied by 2 to the minus 2k, this is multiplied by 2 to the minus 2k, each part multiplied by 2 to the minus k, and this part. So this identity still holds. If z is equal to d times q plus s for integer division, then this identity holds. Now what is this? This is basically z viewed as a 2k bit fraction. So a 2k bit fraction divided by a k-bit fraction gives you a k-bit fractional quotient and a 2k bit fractional remainder. So all the algorithms that will present for integer division can also be used directly because of this correspondence on fractional operands. So fractional z is equal to fractional d times fractional q plus the fractional division multiplied by 2 to the minus k. So there's an adjustment here needed for the remainder. These will become clear as we go through some examples. In the case of fractions, no overflow condition is basically z as a fraction must be less than d as a fraction. Z must be less than d so that the quotient is less than 1. Okay. So here is an example of basic division, integer version on the left and fractional version on the right. So I'm dividing this 8-bit binary number, which happens to be 117 in decimal, by a 4-bit binary number 1010, which happens to be 10. So I expect to get a quotient of 11 and a remainder of 7. And looking ahead, I do get a quotient of 11, 8 plus 2 plus 1, and a remainder of 7. Okay? Now notice that I've written this D, aligned it in the upper half. So I basically multiplied it by 2 to the 4. So what you see here is 2 to the 4 times D. That's because in the recurrence, we need 2 to the 4 times D. Okay, so remember that we need a process for deciding what the quotient digits should be. For now, let's say that there's some magic method that we have. We won't worry about how we came with these choices for the quotient digits. Okay, I'll explain how we do it later. So the third quotient digit, this one is 1. The second quotient digit is 0. The first quotient digit is 1. And the 0th quotient digit is 1. So somehow we know this. Okay? So we subtract Q3 times 2 to the 4 times D. So Q3 is 1 times this number. We subtract, left shift. Subtract 0 times D, 0 times 2 to the 4 times D, which is 0. This is the subtraction result, left shift. Subtract Q1 times 2 to the 4 times D, Q1 is equal to 1. So 1, 0, 1, 0. This is the subtraction result, left shift. And finally, Q0 is equal to 1. So 1 times 1, 0, 1, 0 is 1, 0, 1, 0. Subtract. And we are done. At this point, we have the quotient based on those selections, 1, 0, 1, 1. And we have the remainder, which appears up here. We have to shift it down there because, remember, we said that what the process we discussed leads to the k times s, not the s value itself, but to the k times s, because of those left shifts. Okay, so we have to be aware of this, and at the end realize that this remainder 0, 1, 1, 1 should be written here. So we have remainder 7 and quotient 11, which is correct. Now let's leave it up to you to examine this fractional version. You see that the bits are exactly the same as here. There is the radix point there, which doesn't change anything. We still have the same quotient digit, except they're indexed differently. So this one, instead of being called Q3, it's called Q minus 1, the first fractional digit. Q minus 1, Q minus 2, Q minus 3, Q minus 4, but the values that you see here are exactly the same. Okay, there's this section on program division that I'm going to skip. It has a similar role to that section on program multiplication to basically bring to your attention that in old computers we actually programmed. We didn't have hardware dividers. They were just too expensive to build. So we programmed division. And going through this exercise, programming the division process, provides a better understanding of the division process. So if you have time, you might want to actually go through this section, but I'm going to skip it. It has a loop like the multiplication program, And that loop is executed, say, 32 times for a 32-bit division. So we are talking about hundreds of instructions being executed for one divide operation. Okay, so the first item of business in hardware implementation is to implement that basic division algorithm. And this is known as a restoring hardware divider design. Remember that initially Z is shifted to the left, and then 2 to the k times D is subtracted from it. Now, we need to decide what the first quotient digit should be. Now, in fact, I don't know if you remember the first time you were introduced to long division. Of course, we did it in decimal in grade school. One of the challenging things in doing long division in decimal is that it's non-trivial to guess what the next quotient digit should be. And you may be unsure, okay, should I choose 5? Should I choose 6? Should I choose 7? And it's not immediately clear what the correct choice is. So we sometimes do trial and error until we find correct quotient digit in decimal. Luckily, in binary, the problem is simpler because the quotient digit can be 0 or 1. Okay? So if we guess that the quotient digit is 1, and then do this subtraction, if the result of subtraction is positive, then 1 was the correct choice and we proceed. If the result of this subtraction is negative, then 1 was too large a choice. Therefore, 0 is the correct quotient digit choice. We have to restore. In other words, that subtraction that we did does not provide the correct partial remainder. We have to restore the partial remainder to its original value. In other words, we should not have subtracted anything. So that's why this is called the restoring divider. So we do a trial subtraction, look at the sign of the result. If the result is positive, then we are fine. We should have subtracted and we proceed. The result goes negative, we restore the partial remainder to its original value, choose the quotient digit 0, and proceed. Now, in old computers, the restoration was actually done by addition. So we did a subtraction, the result went negative. In order to correct that negative value and basically restore it to its original value, we did an addition. So do a subtraction, do an addition immediately to restore it. Okay, so this is a hardware restoring divider. The quotient Q is developed in this register. As we guess the quotient digits, we shift them into here. So the first guess is the most significant quotient digit. It moves here. The next guess is the second digit. We shift to the left. Eventually, the most significant digit will move all the way to the left, and we have the quotient built in this register, 1 bit at a time. Okay, this is the double width partial remainder. This is the adder that we use to perform the subtraction by complementing the divisor. So this control signal is permanently tied to 1, meaning that we always choose the complement of the divisor, and we always insert the carry in to form the 2's complement. So we do a subtraction. So this is the trial subtraction result here at the output of the adder. Okay, we only put that value in this register. In other words, we'll modify this register only if this value is positive. In other words, only if the quotient digit chosen is equal to 1. So this is the hardware that chooses the quotient digit. I'll explain it in a minute. So if the quotient digit 1 is chosen, 1 is shifted into this register, and this register is instructed to load the new value. If the quotient digit 0 is selected, then 0 will be shifted into this register, and this load will not be asserted, and therefore the old value is preserved. So restoring divider is a somewhat misleading name here. We don't really restore. We have the old value there. We change it only if it needs to be changed. Otherwise, we keep the old value there. And it needs to be changed if the selected quotient digit is equal to 1, in which case we load the result of the trial subtraction. Okay, so how can we tell whether the result here is positive? Remember that we are actually subtracting from a k plus 1 bit result up here, a k bit result. So the result is positive if this bit is 1, because if this k plus 1 bit result begins with a 1, this value is definitely larger than this value, and therefore the result will be positive. So that bit that was shifted out from the double bit register and is kept in this flip-flop here, so that bit is kept in this flip-flop. It doesn't enter into this subtraction process. So if that bit is 1, then the quotient digit 1 is selected. Okay, or if this carry out is equal to 0, sorry, if carry out is equal to 1. If the carry out of the adder is equal to 1, then the quotient digit, so the quotient digit 1 is selected under two conditions. This carry out is equal to 1, or this bit that was shifted out and is seen there is equal to 1. Okay, very simple quotient digit selection. Okay, now why carry out of 1 represents a positive result? This is a property of two's complement subtraction. So when you add a positive value to a negative value, which is the two's complement of the divisor, the result is positive if you have a carryout. If you don't have a carryout, then the result will be negative. Okay, so this is the simplest divider. It operates for k cycles. After every cycle, it shifts the double width partial products to the left. It shifts the quotient register to the left to make room for the next quotient digit to be entered there. Okay, well, just like in the case of multiplication, where we could share these two registers, we can share them here too, because initially we have the double width partial product and 0 bits in the quotient. Then we shift this to the left, 1 bit opens up here, and we need 1 bit to store the quotient bit. When we again shift this to the left, now we have 2 bits available here, and we need 2 bits for the quotient. So this register, these two registers can be merged so that the partial remainder shares the space with the quotient, because as we need more and more bits for the quotient, we need fewer and fewer bits for the partial remainder. Just to make sure we understand this, let me go back to this example. You see, initially the partial remainder is 8 bits wide. Then it becomes 7 bits wide after we have selected, so that quotient bit goes there in that empty space. Okay, then it becomes 6 bits wide here, 2 empty slots, which will contain 1 0, the 2 quotient. Then it becomes 5 bits wide, and the 3 slots here will contain 101. And finally, it becomes 4 bits wide, and the quotient is now sitting here. The quotient, which is 1011. So the two registers can be shared. And there's never any mix-up between the digits of the two things, because this part of the register never enters into an arithmetic operation. Only the upper half is operated upon. Okay? So those bits can coexist. The bits of the partial remainder and the bits of quotient can coexist in that part until eventually the quotient takes over and occupies the entire lower half. Okay, so this is an example of restoring division. This is the same division we had before. So this 8-bit number is being divided by this 4-bit number, and we have extended it by 1 bit because when we left shift, then we'll have an extra bit there. Okay, so left shift the partial remainder to get this. So basically this 0 goes there, then 3 ones, then 0, 1, 0, 1. Okay, the left shifted version. So I subtract 2 to the 4 times d, or basically add the complement, 2's complement. And this result is positive because the sign bit is 0. And therefore, quotient digit is set to 1. Shift is to the left. Shift to the left. Then again, subtract 2 to the 4 times d. Add the 2's complement. And the result now goes negative. I shouldn't have subtracted. So I restore the partial remainder to what I had up there. And choose quotient digit equal to 0. Because it went negative, the quotient digit should have been 0. Again, shift left, subtract, do the trial subtraction. The result is positive, so that we are fine. The next quotient digit is 1. Shift left, subtract, the result is positive. The final quotient digit is 1. So whenever the result goes negative, we restore the previous partial remainder and ignore the result of the trial subtraction. And here at the beginning, we could have checked for overflow. The high order 4 bits of Z are less than the high order 4 bits of D. Therefore, there's no overflow. It should be strictly less than. Okay, what about sign division? We can do sign division indirectly in the sense of removing the signs, basically turning everything into unsigned, doing the division, and then attaching the signs, appropriate signs, to the result. Unfortunately, we can do this because of the way division is defined. Okay, so when I divide 5 by 3, the quotient is 1 and the remainder is 2. Okay, the remainder is positive. The quotient is positive. When I divide 5 by negative 3, the quotient is negative 1 and the remainder is 2. By definition, the remainder has to have the same sign as z. So if z is positive, the remainder is defined to be positive. If z is negative, the last two cases, the remainder is defined to be negative. So the remainder has the same sign as the dividend. Okay, -5 divided by 3, quotient -1, remainder -2. And -5 divided by -3, quotient 1, remainder -2. So you see that the magnitude of the quotient and the magnitude of the remainder are independent of the signs. So that's why we can do this. Remove the signs. Basically, if one or both operands are negative, just convert them to positive numbers. And then do the division, obtain the magnitudes of the quotient and the magnitude of the remainder, and then attach the sign of z to s, and attach the XOR of the two signs to q. So if the two signs are different, like here, q is negative. If the two signs are the same, up here or down here, q is positive. Okay? So we do an adjustment at the very end. We convert the operands to unsigned or positive, do the division by the algorithm that we discussed, and then attach the appropriate signs to Q and S. We do have direct methods for sign division, but at this point, we already know how to divide unsigned numbers and signed numbers with the signed division done through this indirect method. There's some overhead here because we have to change the signs at the beginning and then a little bit of time at the end to attach the appropriate signs. Okay, the next topic is what we call non-restoring division, which leads to a direct signed division algorithm. So what is non-restoring division? Well, in the previous divider, we basically did a trial subtraction, but we did not put the result of that trial subtraction into this register if the quotient digit should have been 0. Okay, so this basically lengthens we have k cycles in this divider. Each cycle is lengthened by the fact that the decision whether or not to load this register is made after some latency, after this adder has done its work, after this logic has done its work, and we know what the quotient digit is. Whereas if we store a value into that register just when it's produced by the adder, this can be done faster. So this leads to the idea of non-restoring division, which basically says store this value into that register regardless of whether or not it's the correct remainder. Of course, we have to make some correction later. We don't want to keep an incorrect partial remainder here. But we do store. In other words, storing into this register is not conditional upon the sign and this logic. But we always, every cycle, we load the value. So this load signal is tied basically to a constant 1, the clock basically. So on every clock cycle, we load a value. So why is this okay? Why is it okay to load an incorrect value into that register? Okay, this is explained why we can do this and still get the correct division result. So suppose at the start of a cycle, the shifted partial remainder is u. We call it u. Whatever is in that double width register at the beginning of a cycle, after shifting has been done, we call it u. Now suppose subtraction yields the negative result u minus, so I do the trial subtraction from u, this turns out to be negative. Okay? Well, in restoring division, I ignore this subtraction, restore the partial remainder to the correct value u, then double it, and do the next trial subtraction. Okay? So if I were performing restoring division, I would ignore the result of this trial subtraction, restore register to its correct value u, basically subtract 0, then double u, because I'm going into the next cycle, and do the next trial subtraction. Okay? I can achieve the same end result in the register, 2u minus 2 to the k times d, if I keep this incorrect result in the register. So that trial subtraction result is loaded in the register, even if it's incorrect. Then it's shifted to the left, basically doubled. And then instead of subtracting in the next cycle, I add. If I do that, if I keep the incorrect partial remainder, shifted as if, it's the correct remainder, and then add instead of subtract, then I get the same value in the register that I would get after restoring and doing a trial subtraction. So the next trial subtraction is replaced by addition, and it yields exactly the same result. So there's no conditional operation here, at least no conditional operation in the same cycle. In the next cycle, we do have a conditional operation because we subtract if the previous quotient digit was 1, and we add if the previous quotient digit was 0, but this is conditional on something that has already been computed, and therefore does not lead to additional latency. So the idea of non-restoring division is to put the incorrect partial remainder in the register, but remember to add in the next cycle instead of subtract, and that corrects the process, puts it back on track as if nothing had happened. So here's an example of non-restoring division. I won't go through all the details, but basically whenever the partial remainder is positive, we subtract. So here the shifted partial remainder is positive, we subtract. The next shifted partial remainder here is positive, we again subtract. Then the partial remainder goes negative, so means the quotient digit at this stage is 0. At that stage the quotient digit is 0. So notice the quotient digit is obtained with 1 cycle delay. We did this subtraction, and because it turned out positive, we deduced that that quotient digit in that stage was 1. We do this, the result is positive. The result goes negative in the next cycle. So here, we subtract, the result goes negative, so quotient digit should be 0. Because the quotient digit was 0, or because the result is negative, we do addition. The result is now positive, so the next quotient digit is 1. And finally, the last quotient digit is 1. Okay, so whether we add or subtract depends on the sign of the partial remainder. If the sign of the partial remainder is if the partial remainder is positive, then we add, we subtract. If it's negative, we add. So this is example of non-restoring division. And again, there's a check here. 117 divided by 10 gives you quotient of 11 and remainder of 7. So this is a graphical depiction of what is happening in non-restoring division. So we start with the initial partial remainder 117. We double it. So I've written the value in decimal here. We double it, subtract 160. Okay, 160 is basically the 4-bit shifted divisor, which is 10. So 160 is subtracted. We go here. We double. 74 becomes 148. Now we do trial subtraction. The result goes negative, so we restore. So this corresponds to restoring division up here. We restore the partial remainder. Then we double, subtract 160. Double, subtract 160. So the quotient is 1 because of that subtraction. 0 because there was no subtraction there. 1, 1. Now this is what happens in non-restoring division. Double, subtract, double, subtract. The result goes negative, but we keep that. We don't restore it. Okay? Double, negative 12 to negative 24, add 160. And the 136 that we get here is exactly what we got up there. So the process has been corrected already. Then double, subtract. So we keep the negative incorrect partial remainder and double it as usual, but then add to it instead of subtracting from it. This is another view of the same process. So when we do restoring division, Q, the quotient, converges to the correct quotient gradually. When you choose the first quotient digit to be 1, so the value so far is 8, the quotient is 11. So we make progress towards the correct quotient. The next quotient digit is 0. We make no progress there. The next quotient digit is 1. We go to 10, and finally the last quotient digit is 1. We go to 11. So we converge to the correct quotient from below. Whereas when we allow non-restoring, when you use the non-restoring algorithm, here's what happened. First quotient digit is 1. Second quotient digit, we assume to be 1. We do the subtraction. But because the result went negative, we know that the quotient digit is 0. Okay, so it went negative, so we add to turn the remainder into a positive remainder, and then continue. So this detour, basically, incorrect value is corrected in the next step. Now this is a good place to point out that basically you can view this non-restoring division as generating the quotient with digits positive 1 and negative 1. So I can also say that the quotient is, instead of saying 1, 0, 1, 1, the quotient is 1, 1, negative 1, 1. Okay, so whenever I subtract, the quotient digit is 1. Whenever I add, the quotient digit is negative 1. So 1, 1, negative 1, 1. So another view of the non-restoring division algorithm is that it generates the quotient with digits plus 1 and minus 1. So this is explained in this slide. Of course, there's just one complication. If all the digits are ones and negative ones, then the quotient can only be an odd number. You can't represent an even number using just ones and negative ones. Therefore, I may need a correction in the last step of the division. So basically, going to this diagram, here the partial remainder was negative, but because there was a next step, by adding, I made the correction. What if this happened in the very last step? The very last step, the partial remainder went negative. There's no next digit to make the correction. And there I need a correction. I have to apply a correction in that very last step. So one drawback of non-restoring division is that at the very end, you need an extra cycle to make the correction in case the partial remainder becomes negative in the very last cycle, because there's no next cycle to add to make the correction. However, this may be worthwhile because each cycle in non-restoring division is shorter because of the removal of conditional dependency. And therefore, it may well be that 33 of those shorter cycles can correspond to less time than 32 of the longer cycles. Okay, so just because there's an extra cycle does not mean that it will be slower. It can, in fact, be faster. Okay, so here's an example. So if the quotient at some point has the digit 0001, the non-restoring algorithm will decide that the quotient digit is 1 here, and then tries to compensate for that overestimation by generating negative ones as the quotient digits until at some point correction is made, unless we get to the end of the number, in which case we have to apply a correction. Okay, so this is 8 minus 4 minus 2 minus 1, which is the same as 1 in these 4 positions. So this is 1, just focusing on those 4 positions. And this is 8 minus 4 minus 2 minus 1, which is the same as 1. Okay, so the quotient conversion is a process that leads from those ones and negative ones, which is the quotient for non-restoring division, to a quotient that is zeros and ones. Actually, it's a 2's complement number. So to convert from this representation, so this number here is actually a negative number because its first digit is negative. Okay, so to represent that in 2's complement, here is the process. Replace negative ones with zeros. So that's the first step of the process. But this is not yet the correct result. Then shift everything to the left by 1 bit. Complement this most significant bit. And insert a 1 in the least significant bit. So this is the conversion process from a number represented with digits 1 and minus 1 to a 2's complement number in standard binary format. Replace minus 1s with zeros, first step. Shift to the left, and during shifting to the left, complement the most significant bit and insert a 1 there. And I leave it up to you to verify that this 2's complement number is the same as this number. Okay, so here is an example of a non-restoring sign division. basically we can do direct sign division in non-restoring algorithm, because in non-restoring algorithm we already allow the partial remainder to go negative. So it's okay for the partial remainder to be negative at the outset, in other words, for z to be negative, or for d to be negative. In this case, d is a negative value. Z happens to be positive in this example. Okay, so the key observation in this diagram is that the next quotient digit will be selected by comparing the sign of the partial remainder and the sign of d. So if d is positive, then we go back to the original non-restoring. We say if d is positive, we say if this is positive, if not equal means if this is positive, this is negative. If this is negative, choose the quotient digit -1. If this is positive, choose the quotient digit 1. Here, because d can be negative, the decision process involves comparing the sign of the partial remainder and the sign of d. If they're different, we choose -1. If they're the same, we choose +1. And this automatically gives us the correct result, subject to that possible final correction. Okay, so this is a non-restoring hardware divider, very similar to what we had before. In fact, a little bit simpler. The quotient digit selection logic basically takes the sign of the divisor and the carry out from here. And if these two are different, the quotient digit is chosen to be 1. Okay, a quick explanation is needed here. Here we said if the sign was different, the quotient digit is -1. If the signs are the same, the quotient digit is 1. Recall that this will be the carry out will be 1 if the subtraction result is positive. Okay, so this is actually the inversion of the sign, the complement of the sign. That's why I put an exclusive order. Okay, again, these two registers can be shared, can occupy the same space. And again, every cycle we either add or subtract, and this control signal tells us. If this control signal is 0, we add, and there's no carry in. If this control signal is 1, then the control unit decides whether to add or subtract based on the previous quotient digit. If this is 1, we complement the divisor and add 1. So actually this non-restoring hardware divider is a little bit simpler, a tiny bit simpler than the restoring version. It also has a shorter cycle time and therefore tends to be faster. Okay, in this section we discussed division by constants. As was the case for multiplication by constant, optimizing compilers and also VLSI design tools detect division by constant and generate hardware that is much simpler, more energy efficient than an actual divider. So method 1 of dividing by constant is finding the reciprocal of the constant and multiplying. So if several numbers have to be divided by the same value, this would be very efficient because you find the reciprocal only once and then all of your divisions now become multiplications, which is a simpler operation. Method 2 uses this theorem from number theory that says each odd integer d, we only need to worry about dividing by odd integers, okay? Because if you want to divide, let's say, by 10, you can divide by 5 and then shift for the division by 2, okay? So for each odd integer d, there exists an odd integer m such that d times m is a power of 2 minus 1. Okay, so you give me odd integer d, let's say give me 5, d equal to 5. I'll give you m equal to 3, 5 times 3 is 2 to the 4 minus 1. There is always such an m, okay? The theorem in number theory. Therefore, d, the number by which we want to divide, can be written, once we have determined what m and n are, is 2 to the n minus 1 divided by m. Therefore, to divide z by d, I have to divide z by 2 to the n minus 1 divided by m. Okay, I write 2 to the n minus 1 as 2 to the n 1 minus 2 to the minus n. And then I expand 1 over 1 minus 2 to the minus n in the following form: 1 plus 2 to the minus n, 1 plus 2 to the minus 2n, 1 plus 2 to the minus 4n, all the way to infinity. So I've converted dividing by d to multiplying by m, and I already know how to multiply by constants, dividing by 2 to the n, which is basically a shift, and then multiplying by all these factors, each of which implies a shift and add. So shift to the right by n bits and add. Shift to the right by 2n bits and add, and so on. So even though theoretically this has to go all the way to infinity, we can stop after a few terms, because if n, for example, is 4, as we had in the previous example, this is already 2 to the minus 16. The next term will be 2 to the minus 32. The next term will be 2 to the minus 64. And already that's basically too small to make a difference in our calculations, so we can drop all subsequent terms. So I converted division by a constant by multiplication by a constant, a shift, and several shift and adds. The number depends on how many of these terms I have to include. And the number of shift adds required is proportional to log k, because this exponent doubles in each iteration, so pretty soon it becomes too large to matter. Okay, so let's say we want to divide by 5, assuming 24 bits of precision. We have d equal to 5, m equal to 3, as I said before, n equal to 4. And then using that equation, z divided by 5 becomes, after the manipulation, 3z divided by 16, 1 plus 2 to the minus 4, 1 plus 2 to the minus 8, 1 plus 2 to the minus 16. The next term would have been 1 plus 2 to the minus 32. Because we are assuming 24 bits of precision, that's already too small to make a difference. So to divide the number by 5, you triple it. That's basically an addition. This is a shift. Shift add, shift add, shift add. So one add, this is actually shift add as well. Shift Z to the left by 1 bit and add. So shift add, shift add, shift add, shift, 4 shift adds instead of division. Okay, leave it up to you to examine this representation of the shifts and adds. And this slide presents some numerical examples that you can study on your own. Actually, this process for integers is approximate, so it may not always yield the answer that you are expecting. So for example, if you divide 29 by 5, for integer division, you expect the quotient to be 5 and remainder to be 4. Okay? You may or may not get that 5. You may be off by 1 unit, but it's always easy to make corrections at the end. So the process is approximate. And sometimes we actually don't mind that we get the approximate result because we are not doing exact computations anyway. Okay, so this at the bottom of the slide is saying repeat the process for computing 30 divided by 5. See what happens and comment on the outcome. Okay, this last section basically of the chapter prepares us for what will come in subsequent chapters. It's a method known as SRT division. So this diagram basically is a way of representing non-restoring division. Basically, we keep the partial remainder in the range d minus d. And then if the partial remainder is this value, the shifted partial remainder, 2sj minus 1 is this value, I choose the quotient digit 1. If it's this value, I choose the quotient digit 1. And this line indicates the new partial remainder. If the partial remainder goes negative, then I choose quotient digit negative 1. And then the new partial remainder becomes positive in this case. If it's over here, then I choose negative 1. And the new partial remainder will still be negative. So this is basically the lines represent the function sj equal 2sj minus 1 minus q minus j times d. So 2sj minus 1 is the x on the x-axis, on the horizontal axis. And if I'm at this point, that's the value of 2sj minus 1. This is the chosen quotient digit. Okay, and this value must be subtracted, so we get the new partial remainder that is here. Oops. Okay, so here are examples. Partial remainder at that point leads to the choice of qj minus 1 as the quotient digit, and this value, this vertical value, as the value of this, because remember, this line represents that function. So that's the new value of sj. Then if I want to continue the division, I double this. So from here, I go to 1 twice that many. I end up here. Then the next quotient digit will be 1. And this will be the new partial remainder. I again double that. The quotient digit will be 1. This time the partial remainder goes negative and so on. This is known as Robertson diagram. If I complete this process to the end of the division, I get what is known as a Robertson diagram. And on the negative side, a similar thing happens. I choose the quotient digit negative 1. So this is a representation of non-restoring division in which quotient digits are plus 1 and minus 1. 0 is not allowed as a quotient digit. If I want, I can allow 0 as a quotient digit and draw the diagram like this. I say, okay, 0 is easier because I don't have to subtract anything. So in the range where 0 can be chosen as the quotient digit, I choose 0. Where I can't, I choose 1 when the partial remainder is large, and I choose -1 when the partial remainder is large but negative. Okay, so again, if the quotient digit, if the partial remainder, shifted partial remainder happens to be here, I choose 0, and this will be the new partial remainder. Basically, it doesn't change. And then I double that and repeat the process. If the partial remainder is here, then I choose 1. This will be the new partial remainder. So if I want, I can allow 0 as a quotient digit as well. But now the decision process as to whether to choose 0, +1, or -1 is more complicated, because here the decision was based only on the sign of the partial remainder. If the sign was positive, I would choose 1. If the sign is negative, so I just look at that one bit of the sign and choose whether 1 or -1 is the appropriate. Here, I need to establish whether the shifted partial remainder is between these two values. So I need basically two comparisons, greater than this value or less than this value. So this actually complicates the process rather than simplify the process. However, something interesting happens if I do the following. I'm going to limit the partial remainder, instead of to the range d to -d, to the range 1/2 to -1/2. And therefore the shifted partial remainder, which is double that, will be in the range -1 to 1. And then I have this overlap region here. Oh, sorry. I should have pointed to this side. So I need to decide whether to choose 0, in other words, whether I am in this range, to choose 1, whether I'm in this range, or to choose -1. But I want to avoid those comparisons because each of those comparisons is essentially a subtraction and takes time. So here is what I do. Instead of making the decision based on comparing the two as j-1 to -d, I compare it to -1/2 and +1/2. Now those numbers being constant allow simple comparisons. If the result is greater than 1/2, then I choose 1. If the result is less than -1/2, I choose -1. Between those two values, I choose 0. Okay, so now that this allows me to actually do something interesting. So 2s is greater than or equal to 1/2 if it begins with 0.1. So it's positive, the sign bit is 0, and the first bit after the radix point is 1, so this is already 1/2, and therefore this is greater than or equal to 1/2. A value is less than -1/2 as a 2's complement number if it begins with 1, 0. 1 makes it negative, And this 0 makes it basically a small negative, or a large magnitude negative number in this range. So 2s will be less than negative 1/2 if 2s begins with 1, 0. So the decision as to choosing 1 or negative 1 or 0 is based only on these 2 bits. So a very simple logic circuit can make that decision for me. If I see 0, 1 there, I choose 1. If I see 1, 0, I choose negative 1. If I see 0, 0 or 1, 1, the other two cases, I choose 0 as the quotient digit. Okay, this is known as radix 2 SRT division algorithm. Of course, if you look at these numbers up here, the 0, 0 case and 1, 1 case, the digit chosen is 0. Okay? What if I have 0, 0, 0, 0, 3 zeros? Then after I choose the digit 0, I left shift, I still will have 0, 0 here. Then I left shift, I still have, so if there are multiple zeros, if this begins with 0 and there are multiple zeros after the radix point, several digits of the quotient will be zeros in a row. And I can predict that by counting the zeros. If I count 4 zeros, then I generate 4 zeros in the quotient and basically bypass several cycles. If I see 4 ones, similarly, I generate 4 zeros in the quotient and skip those cycles. So this is known as SRT division with variable shift. It's no longer used. It's not very practical. But because you may encounter it in the literature on computer arithmetic, I discussed that. So whenever 2s is greater than 1/2, greater than or equal to 1/2, or less than negative 1/2, we choose these. If it's less than 1/2 in magnitude, or greater than negative 1/2 but less than 0, these are these two cases, I choose 0 as the quotient digit. But then I would immediately be shifting this to the left. So if this next digit is also 0, I will be faced with the exact same condition. So in the top example here, you see there are 4 zeros. So I can generate 5 quotient digits at once, 4 zeros corresponding to these 4 zeros, and then a 1. So in one cycle, I generate 5 quotient digits instead of just 1. So the number of cycles I need for division depends on the statistical properties of numbers in terms of consecutive zeros and ones. And it turns out if you do the statistical analysis, you will have an average of 2.67 digits of Q determined per cycle. Sometimes you're unlucky, you can just determine 1 digit. Sometimes you're more lucky, you can determine, as in this example, 5 digits or 4 quotient digits here. Okay, so that averages to about 2.67. So it's a factor of 2.67 faster division. The downside is that division time will be variable. It will depend on the operands. Sometimes division will be faster, sometimes it's slower. Okay, this example I'm going to ask you to please review on your own. And this final point for this lecture is preview of fast dividers. Remember, we saw that in multiplication, we had a multi-operand addition here. And we mentioned that there are two ways to make this faster. One, generate fewer partial products. That led to high radix multipliers. And the second one was add them faster, which led to both carry save addition and tree of carry save adders. Okay, here we can do the high radix one that we did there. Basically try to determine maybe 2 bits of Q in one cycle. So I need 2 cycles in that case for this 4-bit, 8-bit by 4-bit division. Okay. So high radix dividers is what we will study. Now adding them faster, basically, it's still possible here by using carry save addition, although we can't use tree of carry save additions. We can just do this subtraction, which is basically addition of the complement. We can do this addition using carry save addition, and therefore we don't have carry propagation in every cycle. Then do the next addition using carry save format, and then finally convert the carry save result into the final result. But we'll see that although the idea is simple at this abstract level, it leads to complications, because to estimate what the next quotient digit will be is not straightforward when the partial remainder is kept in carry save form. Remember, for example, in non-restoring divider, we use the sign of the partial remainder to decide what quotient digit to generate next. But the carry save number, the sign is not easily determined, because the carry save number has 2 components, and without adding them together, you really are not sure about what the sign is. Okay, so dealing with that complication is a subject for the next lecture. Okay, that's all I wanted to say for basics of division. See you in the next lecture.